Let's take the function f of x equals x to the fourth minus 4x to the third and talk about the concavity of this function. First, let's find the possible points of inflection. Possible points of inflection are points that have an x value where the second derivative is equal to 0. So we'll begin by finding this function's second derivative. This is fairly straightforward. We can use the power rule on each term in this function. The derivative of the first term is 4x to the third, and the second term's derivative is 12x squared. The second derivative follows as 12x squared minus 24x. To find the possible points of inflection, you set the second derivative equal to 0. The easiest way to solve this equation would be to factor a 12x out to the front, which leaves you with x minus 2 as the other factor. And this means that the possible points of inflection come from x values where 12x is equal to 0, x equals 0, and where x minus 2 is equal to 0, x equals 2. The x values of the possible points of inflection are 0 and 2. We'll use those two values to find the intervals of concavity. 0 and 2, those x values, break apart our function into actually 3 intervals. The first interval goes from negative infinity to 0, the second interval from 0 to 2, and the third interval from 2 to infinity. So this function will either be concave up or concave down the whole time from negative infinity to 0, and then it will be concave up or concave down from 0 to 2, and it will be concave up or down from 2 to infinity. It will never change concavity inside of these intervals. The only possible place where it could change concavity would be at x equals 0 or x equals 2. To test the concavity in each of those intervals, to determine if each interval is either concave up or concave down, you're going to pick a number in each interval and put it into the second derivative. If that yields a positive number, you know that that entire interval is concave up. If it yields a negative number, you know that that entire interval is concave down. A number between negative infinity and 0, that's easy to work with, is negative 1. Substituting a negative 1 into the second derivative, I'll use this version of the second derivative. 12 times negative 1 is negative 12. Negative 1 minus 2 is negative. Negative times a negative is a positive. It's not really important even that you identify exactly what the value is. If you're sure it's positive, that tells you that from negative infinity to 0, this graph is concave up. So when I state the intervals of concavity, I can say that this function's graph is concave up from negative infinity to 0 because an x value in this first interval from negative infinity to 0 yielded a positive number. If I would have picked negative 2 or negative 3 or negative a million or any number between negative infinity and 0, I would have got a positive number back again. The function is concave up from negative infinity to 0. How about from 0 to 2? Just because x equals 0 is a point of inflection or a possible point of inflection, that doesn't necessarily mean that the graph will change concavity here. Let's test and see. If I choose a value in the interval from 0 to 2 and substitute that into the second derivative, I would get, in this case I'll pick 1, and I will get 12 times 1 is 1, or 12 rather. 1 minus 2 is negative 1. 12 times negative 1 is negative 12. The important thing is that it is negative. That tells me that this function's graph is concave down in this interval. From 0 to 2, this function is concave down. How about from 2 to infinity? Well, I can pick any value from 2 to infinity. It doesn't matter what number I pick. I'll choose a 4. 12 times 4 is positive. It's 48, but that's not super important. If I just know that it's positive and that's being multiplied by x minus 2, 4 minus 2 is also positive. A positive times a positive is a positive number. That's enough information to tell me that this function's graph is concave up from 2 to infinity. So the intervals of concavity, it's concave up from negative infinity to 0 and from 2 to infinity. It's concave down from 0 to 2. Because the graph changed concavity at x equals 0 and the graph changed concavity at x equals 2, both of those are actually x values for points of inflection. This function's graph has 2 points of inflection. One point of inflection occurs at 0, at x equals 0, and the other point of inflection occurs when x equals 2. So I'm going to write those points of inflection as ordered pairs. I'll substitute a 0 into the original function to get the y-coordinate of the point of inflection that has an x-coordinate of 0. And I'll substitute a 2 into the original function to find the y-coordinate of the point of inflection when the x-coordinate is 2. F of 0 is equal to 0, so one point of inflection is 0, 0. F of 2 is negative 16, so the second point of inflection is 2, negative 16. This graph has 2 points of inflection, 0, 0, and 2, negative 16. We can verify our answer by taking a look at the actual graph of the function. We found that there were 2 points of inflection, one at 0, 0, and one at 2, negative 16, which would be difficult to identify by just looking at the graph, but it certainly makes sense that this point has an x-coordinate of 2 and a y-coordinate of 16. Notice that the shape of this graph, it's concave up from negative infinity to x equals 0, as we confirmed. It's concave down from 0 to 2. We're talking about x values here, and then it's concave up from 2 to infinity. This graph will continue to the right, concave up.